Now that we understand how many electrons are in atoms, what we're going to do is look and see what happens when atoms bond to each other. And because the electrons are on the outside of the atom, that's what interacts when two atoms collide. What we're going to see is that electrons in one atom are attracted to the nuclei of others. And what happens there, if it can happen, is the whole basis of bonding. First, you need to understand that there are some atoms that never react in reactions, at least as far as we're concerned. Those are the noble gases. That's the farthest column on the right, topped by helium, and that goes on down. All of these, except for helium, all of these have what we call an octet in the outer shell. And what we have found is that any atom that gets that octet, a similar electronic structure to one of the noble gases, has stability that's given to it by attaining that octet. Now, gaining and losing electrons takes a lot of energy, but when you have an octet form, the amount of energy is less. And so what we see is those atoms will react in a way that gives them this octet. Okay, so when atoms react, they gain some stability by changing their valence shell to an octet. When we're making ions, we're either losing or gaining electrons. And what we find is that the atoms that have 1 to 3 electrons in the outer shell lose those electrons, and then all you have are core electrons, the ones underneath the valence shell. And those are an octet, so it gets some stability from that. Atoms with more than 4 electrons usually gain enough to have an octet. There's an exception to this. Tin and lead actually will lose 4 electrons, but it's a real high energy state. That's a lot of charge in one little atom. And it does happen. But this is a good rule here. 1 to 3 electrons are going to lose them. More than 4, they usually gain them. Gaining electrons is done with nonmetals, and the losing of electrons is always done with metals. You can also make bonds by sharing electrons to give an octet. The first thing we're going to look at is going to be the ionic bonds, but let's just look first at what is the difference between an ionic bond and a covalent bond. When you have an ionic bond, the elements are actually losing and gaining electrons. The metals are always going to lose electrons, and the nonmetals always gain electrons. So in any compound that is made of metals and nonmetals, the metals have a positive charge and the nonmetals have a negative charge. When you have covalent bonds are typically between nonmetals. What happens is the elements react by overlapping their orbitals and sharing electrons. We call it a shared set of electrons. And so the overlap allows both atoms to have the electrons in their valence shell, and through that sharing, they get this octet that gives them stability. We have some bonds that are mixed ionic and covalent, but you don't have to worry about that. We're not really going to discuss it too much besides this. Now, how do you know what type of bond is there? It's relatively easy. If it's between a metal, which is on the left, and a nonmetal, which is in the upper right, we consider that to be ionic. And if it is between a nonmetal and a nonmetal, then we consider it to be covalent. It's a gray area. Purely ionic and purely covalent aren't very many bonds like that. But it's not a perfect description, but for us, this works. Now, ions are going to be atoms that have lost or gained electrons compared to their neutral state. Remember, only the electrons, the numbers of electrons are changing. The number of protons in the nucleus remains the same, so it remains the same element. So if potassium loses an electron, it's still potassium, but what does change? The number of electrons, and so the charge is, there is a charge on that atom, and then we call it an ion. And just before we go into this, I'm going to start using reaction arrows, and sometimes people have trouble understanding these. And what I'd really like you to do is look as a reaction arrow as saying time elapses, and it separates the before and after. So if you look at this example below, you have a pregnant woman, time elapses, and it's a woman plus a baby. Here's another. You have a sperm and an egg. They're separate. Plus always means that it's separate. It doesn't mean they're added to each other. It means they're separate. So you have a sperm and egg. With time, what happens? It becomes a zygote. So it's basically showing before and after. If you keep that in mind, it might help you understand what's happening better. The formation of a cation comes about by an atom losing electrons. So let's just look at carbon-13 down here. I just picked that for the fun of it. But carbon-13 has what? 7 neutrons, 6 protons, and 6 electrons. We know it has 6 protons because if we look in the periodic table, carbon has atomic number 6. I chose this isotope just so that I would have a different number of neutrons. Notice what happens before you have this uncharged atom. Afterwards, what happens? Now you have a charged atom. It has a positive 1 charge because it lost 1 electron. So many people think if it loses, it has to become negative. But remember, electrons have a negative charge. And if you look in this atom after it loses an electron, you have 6 pluses and 5 minuses. 6 plus and negative 5 gives you positive 1, which is a charge. Anions come about by the gaining of electrons. Here we're going to take that same atom and we're going to add an electron to it. Notice, remember, this plus means these two are separate. Just like here, this plus means there's a carbon plus and an electron somewhere else floating around. So here we get 1 electron from somewhere, and when we join it up with carbon-13, it can jump into its electron structure. And what do you see? Now you have an additional electron inside the atom, and because there's 6 pluses and 7 minuses now, the overall charge is a negative 1. So keep in mind, loss of electrons gives a positive charge, gain of electrons gives a negative charge. Students get very confused on this, so keep it in mind.